So if I could just jump ahead a little bit here, as a statistician, it seems like if we got a raw signal of some sort, then our goal is to estimate what these C's are.
Yes, not just estimate, like compute them.
Compute them. Okay. Yes.
Yeah, I guess in the real world, you'd have to use some kinds of approximation, so it really would be an estimation. But in this case, we can like it's not just an estimation; we're finding out exactly what they are.
Right. Okay.
So
because this part is defined. This part.
Yeah, that's set.
That's set.
You just have some fundamental frequency 1/t,
right.
And this is the same for every single value.
Right.
Now, some of these k's could be 0, as we'll see, but you still have they will always come in those intervals.
Yes. Okay.
Okay. So first, I want to define the idea of orthogonality.
Okay.
So two signals are orthogonal. The integral of 0 to t, e to the j 2 pi kt over big T. I'm going to check to make sure I'm writing this right. E to the j 2 pi lt big T dt. Let me just check.
It has been quite a few years since I've taken ordinary differential equation, so I can't quite help you out here just to make sure that this is right. But I do remember that you can define orthogonality for two functions.
Yeah.
By computing the integral of their.
Just put a minus sign here. Yeah.
Of the product of the two.
So the minus sign just makes this math a little easier.
Okay.
Equals. So it equals 0 if k does not equal L.
Okay.
And it equals. It equals t if k
is equal to
L.
So what is the significance of this? I understand the orthogonal definition. This mirrors what we know from linear algebra. If you have two vectors, and you take the dot product of them, and if that's equal to 0, by definition, those two vectors are orthogonal.
Right. Well, I'd like to say one thing. So the dot product is just a special case of the inner product.
Yes.
And the inner product, the dot product is for vectors, but the inner product generalizes to functions, for example.
Yes.
So this is a case of the inner product of two functions. With these vectors, we do the dot product. So this is just a way to generalize that. And now what this is doing is basically we know that, for example, sine of t and sine of 2t are orthogonal.
Okay.
And you can look at this by they're integer multiples of each other's frequencies.
Okay.
Yeah.
Okay.
And so if we were to multiply them and take the integral, we would get 0.
Okay. That's something worthwhile for me and everybody else to try to work out. Okay. All right. So intuitively, physically, what does it mean for two signals to be orthogonal to each other?
That's hard to say. I would just say that in the vector space of functions, they are orthogonal, and it's not something we can visualize that easily.
Okay.
But just as in two-dimensional Euclidean space, you could say that these two vectors are orthogonal.
Okay.
In a sense, the functions are orthogonal in that way, and we just define orthogonality for functions as being if we take the product of the two functions and integrate over one period.
Okay.
If it equals 0, then they're orthogonal.
Okay.
That's just how it is.
Okay. Let's leave it at that. Okay.
Leave it at that.
Sounds good. Okay.
Okay. So now that we have this definition, this is useful to know. So, what we can do is.
Should we erase this?
Leave this up.
Leave that out. Okay.
Yeah. So we want to solve for these c sub k's.
Yes. Okay.
So let's multiply each side by e to the minus j 2 pi k little t over big T.
Right, because based on what we just learned about orthogonality, if we multiply that by e to the minus j times 2 pi kt over big T, then that should equal to 0?
Well, we'll see.
We'll see. So, okay, sorry.
Over big T. e to the minus j 2 pi, or sorry, we'll do LT.
I'm so anxious that I can't really resolve my anxiety.
And I forgot to multiply on this side, s of t e to the minus j 2 pi LT over t. Okay, so we have this, but then remember orthogonality was defined when we take the integral.
Right, you got to take the integral.
So we need to take the integral.
Okay.
And the way I'm going to do this is I'm going to put the integral here.
Okay.
So we're taking a finite sum, or well, it's an infinite sum, but we're doing a summation of integrals.
Right, because the stuff on the left does not depend on little t.
Right.
So we can just integrate this stuff.
Correct.
Right.
Yeah.
Okay.
The c sub k's do not depend on t. So,
right.
So we'll just do this 0 to big T dt, and we'll do the same thing over here.
Right.
Sorry, this is a little messy.
Yes, I forgot earlier that you're supposed to integrate. You can't just multiply them and right. Okay, you got to integrate.
Yep.
Okay.
Yep. So we're going to sum over all these terms. Now we just said that these terms are going to be 0 unless k equals L.
Right. Okay.
So we can just consider the case when k is equal to L.
Okay.
So this summation goes away. We just substitute k for L.
Right.
And this equals big T.
Right.
So then we get, so I'll write it over here. So we get big T, C sub k, or it's L, sorry, because we're substituting in L, equals integral from 0 to big T, S of t, e to the minus j 2 pi LT, dt.
Sorry, so how did you go from here to here?
So I just took, this all equals t. So for every,
yes, that's right. If k is equal to L, then this whole thing equals to t, right?
This summation goes away because it's just one term.
Right, it's just that one term. So that's okay. Yeah.
T, and then this is not really k because it's an L because I'm considering the Lth coefficient.
Yeah.
And then this is just what it was before.
Right. Okay.
And then what I'm going to do is I'm going to just move this t over so we solve uniquely for the coefficient.
Ah. Okay.
So now we can solve for the c sub k's.
Right.